Hello. Today I'm going to talk about your final project, which is basically rainfall runoff modeling and using rainfall runoff modeling for flood hazard analysis. Let me uh, clear everything in my MATLAB, so I don't have anything in my workspace and anything in the command window. Let me start with a little background of what is basically rainfall runoff modeling. Okay, no, this is not gonna work. No, all right, you don't have to go to presentation view. So I don't know how much you're familiar with this water cycle, but what happens is that you have the sun. There is energy coming in from the sun, and you have the oceans. Water would evaporate from the oceans, and then it will come to the land, and it will precipitate as snow, as rain, etc. And then that water is routed through the valleys. We'll have some stream flow. We'll have evaporation. There's so many different processes involved in this water cycle, which we are not really focused on in this course. So I'm going to try to simplify everything. So in terms of stream flow, what happens? We have the mountains, we have the precipitation as snow and rainfall and everything. So that precipitation is routed into some streams. There are evaporation from the stream. There are transpiration from the trees. Trees extract water from the groundwater, which is connected to the streams. So there are all sorts of processes involved. What we care about is basically this stream flow prediction. So what we want to know is if temperature is this much. So temperature will gives us this evaporation and transpiration. You can imagine that when it is warmer, there's more evaporation, there is more transpiration if there is water. Uh, and there's more snow month if you have snow. So we can, all these processes take part into creating this stream flow. We are interested in predicting this stream flow. Why is it important? One of the issues that we have with these streams is you all have heard of this inland flooding. If you remember, in 2017, Boise River was flooded, so the amount of flow in Boise River was more than the capacity of the river. So what happened? So basically, that's the definition of flood. When the river, inland flooding at least, or terrestrial flooding, when the river has more water than its capacity, then the water comes out of the river channel, and it will flood the areas around. So in this case, you can see these cars are all underwater because the amount of water in the river is more than what it can tolerate. And why do we care to predict this? Because if you don't predict this, and if there's someone in here, there's loss of life. So it's very important that we predict what is going to come, what stream flow is going to come toward the city, and we use that for all sorts of hazard analysis and for warning purposes, etc. So basically, again, coming back to this water cycle, we care to model this stream flow. Again, there is some precipitation coming in, there is surface runoff, and then some of this precipitation is absorbed by the vegetation. Some of it infiltrates to the ground, and then some of it would even infiltrate further down, which is percolation. So we have infiltration, and then we have percolation. And so if the soil is wet, part of the precipitation will come out as surface runoff. So we have surface runoff coming through the stream. We have infiltration routed through the soil, and then part of that infiltration comes back up, and then we have this percolation. So that shallow groundwater, deep groundwater, part of that will come back to the river and will constitute this stream flow. What we want to do, we want to model this stream flow. Again, all sorts of the processes that we discussed, the evaporation, the overland flow, interflow, which is that shallow groundwater, and base flow, which is that deep groundwater recharge. So part of that goes down, part of it comes back up. There is overland flow, there is evaporation, there is transpiration. Everything is here, and all of this will create this stream flow that we are interested in. But how can we model this? So all these processes you can write equations for, but at what scale? One would say, I would consider all my so the entire basin, basically from the mountains of Boise River all the way to the station in Boise, the gauging station in Boise. I would consider everything as one single bucket. So how much water I put in, how much water comes out of that bucket. That's the simplistic way of looking at it. This is called lumped modeling. So everything is considered one bucket. Water is added to the bucket, water evaporates from the bucket, water is routed through the bucket, etc., etc. Everything is one single point. We have more complex models. We have semi-distributed models that each section of the river is considered one watershed. So it's basically like lumped, but each section is considered a different watershed. And then all of them will add up and water will be routed, and it will give us the stream flow. And there is more more complex models like distributed models. We have some grids, so grids are even smaller than the sub-watersheds. So we run all those processes at each of these grids. Again, this is not a hydrology course, so I'm not going to go into too much detail of what is this hydrologic modeling and stuff. What we are focusing here is basically this lumped conceptual model. There are so many different conceptual models. Basically, conceptual models simplify all those processes that we discussed. Remember all these processes? Simplify all these processes into a couple of buckets. There are so many different models of or there are so many different conceptual rainfall runoff models. One of the simplest ones is called GR4J model. What it does, it will take the precipitation, it will take the potential evapotranspiration. Potential evapotranspiration means that if we have unlimited amount of water, let's say we have a lake, how much water from that lake would evaporate into the atmosphere. So it will that depends on precipitation, that depends on temperature, wind, and a couple of others. So basically what GR4J and any other of these conceptual models do, they will take precipitation, they will take potential evapotranspiration, they will take temperature and stuff, and then they will route this precipitation into several buckets and give us a stream flow. So this precipitation is absorbed by the vegetation. Part of that vegetation water would evaporate back, transpiration, evaporation. Part of the surface flow, part of the water in the surface soil will evaporate, and then part of it will go down into the ground. So anyway, so what happens is that we have different buckets, we have different processes. Those processes are simplified. Precipitation comes in, evaporation goes out, and the model will give us the stream flow. But this model has some parameters. As you can imagine, these buckets don't exist in the reality. So what we have is we have some buckets, we have some parameters for each of these processes that we define, and we don't know the values of those parameters. Basically, what we need to do is we need to observe what goes on in a watershed, like a Boise River. We observe how much precipitation we had over this region, how much stream flow we had, and then what we will do, what was the temperature, etc., etc. We will give all those values, precipitation, temperature, etc., and then the stream flow. We'll give it to this model. We'll give the precipitation and temperature, etc. We will change the values of these parameters so that we get a stream flow that is close to what is observed at our station. So basically, what was the stream flow in Boise River, and what is the model giving us. So that's called, that process of tuning parameters called model calibration. If I want to give you more, give you an example, what we have is this watershed, and we have this model. We have the observed input, which are precipitation, temperature, etc. We have the observed stream flow, and then given this model, we can simulate the stream flow. So if this is our observed stream flow, given some parameter, just random parameter, we will see what is the observed stream flow. And then what we will do is we will change the parameters of this model so that our simulated stream flow is closest to the observed stream flow. So that is called the model calibration problem. Now with this, I will start looking at the code that I provided to you. That model calibration is basically what we want to accomplish with this final project. What is provided to you is, what are provided to you are all these files. So we have a file called, or a function called gr4j. We have a function called initialize, a function that is called main. You will not have this main answer. That's what you will create, which is basically modifying this main to create this. You have the project description, you have the snow module, and then you have the watershed.txt. The snow module is basically a function that tells you, when you have precipitation, when you have snow coming down, if the temperature is low, it's below freezing point, the snow will accumulate. If the temperature is above freezing point, the snow will melt and will come down as stream flow. So basically this snow module will translate how much of your precipitation is going to become snow and how much of that snow will melt and come down to stream. The main model that you deal with is this gr4j. Let's go through this main.m and let's see what we have here. CLC clear, you already are familiar with. This is basically how we define the pass of data. PWD is basically giving you the current directory. So this is in my folder C, under folders users, Mushtaba Saleh, Dropbox, courses, etc., etc. That's the current directory that I am in right now. So PWD will give you the current directory. And then if you add / watershed.txt, it will tell you where this data, this watershed.txt, where is this data in. So if you have Mac, then this / will not work for you. You have to use / because / is for Windows and Linux and / is for Mac. Anyway, so if you're using Mac, change this to /. Then what you have, what is asked from you is from what year to what year do you want to calibrate your model? Because oftentimes we have, I don't know, 10, 15, 20, maybe 50, maybe at some cases even close to a century of observations for a river watershed. We don't want to use all those data for calibration. What we are going to say is, you know what, just from January 1st, 1980 to January or to December 31st, 1982 is the time that I want to use the data for calibration. So I'm going to use the data, the precipitation, temperature, etc. from this time. I will run those through my model, and then I will tune the parameters of that model so that I will get the same stream flow out of my model similar to that of the observations. My model name is gr4j. That's just the conceptual Rainfall runoff models. Then what happens later is this function initialize will be run. Initialize is basically this function that takes the pass of your data, the first day of calibration, last day of calibration, and what model was used. And then what we have, it will assign these parameters into some structure parameters, structure variables, and I'll tell you a structure variable in just a second. Give me a second, I'll tell you what that is. What this function will also do, it will read the data. So this watershed.text, it holds the data. The first column is year, the second column is months, the third column is day, the fourth column is precipitation, fifth column is potential evapotranspiration, sixth column is flow, 7 and 8 columns are minimum temperature, minimum daily temperature, and maximum daily temperature. So it will take all those data, these are all the inputs to the model, and then it will find what row of that data. See, remember I did 1980, January 1st, 1980? It will find what is January 1st, 1980, what's the index of that in this data. So it will find the index of this, which is 2079, row 2079, and then it will find the index of the maximum. So 3 years later, what's the index of data for that? And then this is basically some reformatting. It will assign the dates into data. Again, these are structure variables, and I'll tell you what structure variable is in just a second. Then later on, it will show you what is the minimum value for a variable in that model and what is the maximum value for the variable. So what we'll do, we'll tune the variables, right? But we have to have a bound. So this variable might, like for the first variable or the first parameter of the model, it changes between 0 and 1500. That variable cannot be negative. So you have to have bounds for those. And then initial states is basically, if I go back to this model, so remember these buckets, how much water is in this bucket basically. So that's just the variable that we have to define, and you don't really have to worry about these variables. These are just, I'm just trying to explain some background to you. It doesn't mean that you have to know all this stuff. It's a matter of you being able to use these functions and you be able to optimize the parameters of this one. Let me run these lines so far and explain to you what structure variables are. So see this minimum max t calib, if you look at it, see this couple of boxes. If you look at this one, it's like one line coming in and becomes several lines, like a fork. This means that there are more variables under this par range. So par range, if I open this par range, you see that there is a mean and there is a max under par range. And if I open up this handles, which is another structure, you see that there is handles.model is one variable, handles.data is one variable, handles.area factor. So that dot is basically, if I go back here, see this dot? This dot means that this variable mean or min will be under the umbrella of par range. Max will be under the umbrella of par range. That's what you see here. If I open this up, you see par range.min, par range.max are right here. These are structure variables. Sounds good. So I run all the way to here, but now let's go back to this optimization problem. How do I find this parameter that fits my data? Where do I find it? How do I find it? What do I do with it? One thing that you can do is you can randomly sample from the range of parameters. So for the first parameter in GR4J, you notice that we have between 0 and 1500. So what you can do is basically you can say, maybe my parameter value is 10. Maybe my parameter value is 100. Maybe it is 150. Maybe it is 180. Maybe it is 200. So you can sample, I don't know, 200 of those values. And then run your model for each of those 200 samples of parameters and see how close is your simulation, this green line, to your observation. So that's one way that you can find what is the parameter value. So basically randomly select some parameters, run the model, and see where the model is closest to the observation. One way of doing this random sampling is called Latin Hypercube sampling. Latin Hypercube sampling means that if you select 5 points in this two-dimensional, because GR4J has 4 parameters, so it's a 4-dimensional problem. And then we have 1 parameter for the snow module, so we have 5 parameters. So overall, my model has 5 parameters. That's a 5-dimensional space. This is a 2-dimensional space. If there is another dimension, there is a 3-dimensional, so X, Y, Z, and then 4-dimensional, 5-dimensional, etc. What happens with Latin Hypercube sampling is that it will randomly select points from everywhere in the space. Because let's say we have 4 random points, right? Maybe all those 4 random points can cluster here, or here, or here. If all points are clustered here, and then my true parameter value, the one that provides the best answer, is here, then I cannot find it. But if I have Latin Hypercube sampling, then I have parameters from everywhere in the space, and then you know, there is a higher probability that we find the best parameter value. So this LHS design will give you that Latin Hypercube sampling parameters. So what it takes is, it will take how many samples you want. You know, you can put 1,000, you can put 10,000. Actually, I asked for 10,000, so let's do 10,000. And then, you know, how many parameters do you have? What it does, it will give you some random variables between 0 and 1 with a dimensionality of your parameters. In this case, we have 5 parameters, so we have 5 dimensions. So we'll get 1,000 times 5 random parameter values. So if I evaluate this, or 10,000. 10,000 times 5 is the number of random parameters that I get. Then the issue is, these are between 0 and 1. These are all between 0 and 1. We have to map these between the minimum parameter value and the maximum parameter value. So what I will do, if you remember in class we talked about this, we will take the minimum value, we will multiply that random value by maximum minus minimum, and that will map 0 to 1 into minimum parameter value to maximum parameter value. So what I will do now is I will evaluate this, and if I show you, where is it? Yes, here. If I show you this now, you'll see that those values, those between 0 to 1 values are now mapped into, for example, for the first parameter is mapped between 0 and 1500. Say we have 100, we have 200, we have, I don't know, 600, 1300. We have everything between 0 and 1500. Sounds good. So this is my parameters, and then now for each of those parameter values, what I can do, I can evaluate my model. So I evaluate my model for each of those parameter values, and this is what does the trick for you. So this line will basically take the data, the model parameter, and the initial states into your model, and it will give you some sim fluxes and simulated fluxes, simulated states. We don't care about simulated states. Only thing that we care about is these simulated fluxes, which is basically what is the streamflow value. And then to get the streamflow value, we can translate these fluxes into the total channel inflow, TCI, which is basically streamflow. So if I evaluate this, you will see that I now have a TCI for 3 years, 3 times 365 days almost, or roughly. I have about 1,096 days. So for each day I have a simulated streamflow, and then I can compare that simulated stream flow to my observed stream flow. So the first day, my simulated stream flow is 1.44 cubic meter per second, and my observed is 0.05. Then second day is 0.04, it's 1.42. What we need to do, we need to get these closest to one another. So that's the part that we will do later. And then what we can do, when we have the stream flow, and so we have the modeled stream flow, we have the observed stream flow, we can calculate the residual. If you remember from class, simulation minus observation, or the other way around, will give you residuals. And you can also calculate R squared, which is 1 minus sum of residual squared divided by sum of flow minus mean of flow, observation minus mean of observation squared. So that's our R squared value. And then we can also plot this simulation, and we can plot the observation on top of that. Simulation is with whatever color it comes out, with a line width of 2, and observation come out as red dots. And then axis goes between 1 and 1096, which is how many days we have, and it goes y goes between 0 and maximum of whatever TCI or flow is. It's just to constrain the figure, and then we can add X label, Y label, legend, etc. to all this. So if I run this, what I will have is, well, let me get rid of this. That was a previous figure that I had. What I have is basically these red dots are my observations, and this blue line is my simulation. As you can see, this is a random simulation, random parameter value, so the fit is not really that great. If I run again, then now I'm overestimating this stream flow. The fit is not really great. Now I get a better simulation. It's closer to what it should be, but still not great, but not too bad either. So if I continue doing this, if I do this 10,000 times, then I can find a couple of simulations that are close to my observation. So if I do this 10,000 times, this is bad. The previous one was good, so I accepted the previous one. I run this again, not good. I run this again, not good. So I keep doing this. Oh, well, okay, but not really. Not good. Not good. Then you can see this is just, you know, it's you don't want to sit behind the computer and do this 10,000 times. It's gonna take you a couple of days, maybe a week to do that. So you want to use the while loops and the for loops that you learned before, right? So you don't really want to sit there and do this over and over. This brings me to this main answer, which you don't have access to, and this is basically my work on this file main, and then that's what you will do. What you will do all the way to here, to creating random parameters and model parameters. So you'll need to have 10,000. So in the main file, if it is 1,000, make it 10,000, and then you have your model parameters. Everything is good. What you will do is, instead of running like run, what you'll do, you'll have to have a for loop. For loop that goes, so you have j goes from 1 to 10,000, because I want to run this 10,000, run the model 10,000 times. This line will run the model for you. What happens here is that this handles the data is fine. That's what you know, that's the data that goes in. In the file that you have, you're only evaluating your model for the first random parameter. This is the first random parameter. See what we have here? We have 10,000 random parameters, and each random parameter has 5 values in it. So that's a vector of 5 values. We have 10,000 of that. So this, in this main, see, we are only taking the first one. What we want to do is, since we are gonna run this model 10,000 times, we want to take the first parameter, the second parameter, the 10, the third, fourth. We want to evaluate all those parameters. The issue is this is now a string, and then I don't want to confuse you with all the strings and stuff. The only thing that I want to draw your attention to is this one is now a string, whereas what I have in mind as one is a double, or is just a scalar, just a number. It's a double value. It's not a string. What we need to do is we need to put this comma dot comma sorry, apostrophe comma num2str of j. This num2str will change number to a string. So this j, remember in the for loop, that's 1 2 3 4 5 all the way to 10,000. This will change each one of them into a string. So that one that was previously a string before is handled here. This num2str of j within these two commas and within these two apostrophes will handle that for me. Then, so each time you're running this model, you will have one set of TCI. See, this TCI, total channel inflow, is I have 1096 days, one column. So that's for the first parameter value. Then we'll have the second parameter value. This should go to the second column. For the third parameter value, it should go to the third column. So for 10,000 runs, I will have a matrix of TCI, which is of size 1096 by 10,000, because I will have 10,000 columns. Each column is basically representing one of the parameter values. So what I will do here, I will do TCI of double dot. So whatever is in the column is fine. I will put the j's. So first will go to the first column. Second model simulation will go to the second column. Third model simulation will go to the third column. Fourth model simulation will go to the first column. All the way. The 10,000th model simulation will go to the column of 10,000. And then this is just basically translating whatever that TCI is into a Streamflow. You don't care too much about that. What you also will do, for each of those model simulation, you will calculate the residual. See, I do this J because for each model I want to separately calculate what is the residual. And then with that residual, I will have R2 of 1 comma J, because the J's models, the J model simulation of number J has model simulation of TCI J, Streamflow J, column J, and then it will be translated into R squared of column J. So each column in TCI and R squared is associated with these parameter values, these rand pair or model pair that we have. So this will calculate R squared for the J's parameter in this case. So this is basically the modified version of this, but now you're automatically running 10,000 times. Now that you have 10,000 times, let me run this, because this is going to take a while, and then I'll explain to you what these lines will do. Alright, so back to these lines. What we have is basically we have a bunch of R squared values. We'll have 10,000 R squared, and as you can see, it's still busy, so it's still running. A bunch of R squared values, I'll have 10,000 of them. If you remember, R squared values, the best R squared is 1, and the worst R squared is negative infinity. So it goes from 1 to negative infinity. The higher it is, the better the model simulation. So what I will do is basically I will sort my R squared in a descending order. So sort R squared in a descending order. And then I need to show you something, because I want to get the index of the sort as well. We've talked about this in class, but regardless, I want to show you again how this index thing works. So I'm going to open up another MATLAB. This is busy. It's not going to work now. On this MATLAB is not going to work. I'm going to work on another MATLAB. So okay, so this is now open. I define A as being 1 4 3 9 0 9 6, again I don't know, 5 10. So if I just do sort of A, it will sort it from the lowest to the highest. If I do sort A descend, it will sort it from the highest to the lowest. But the issue is, it will sort it, but I don't know. So this 10 was element 1, 2, 3, 4, 5, 6, 7, 8. So this 10 was element 8, and now that's element 1. I don't know what was the original value. And in our case, in the modeling case, is that when we sort them, we want to know which parameter it basically created that R squared. So I really need to know what was the index of the original value. So that's what I do here, is sorted A, and ID index of A is equal to sort A in descend. And so it will give me what is the maximum value and what was the index in the original associated with that maximum value. So that's what I need. Alright, so my run is done, but let me put this aside for now and I'll get back to this. So what I will do, I'll sort my R squared values in a descending order. It will tell me what is the R value or R2 value and what is the index associated with that R squared. So I ran my model 10,000 times and I will select the first 1,000. The first 1,000 in this index X is basically the best 1,000 R squared values. The best 1,000 R squared values. So, and I will find what is the total channel inflow associated with that first 1,000 or that best 1,000 simulation. Best 1,000 simulation is those highest 1,000 R2 values. Index from 1 to 1,000. And just to show you, index of 1 is not going to be 1. So simulation number 4,205 is my best simulation. Then my simulation, the second best simulation is simulation 1,737. So I will select all those columns from my TCI. So all the rows and the best 1,000 columns from TCI will be saved under TCI index. One of the things that I asked as an output is TCI range. So basically I want to know for each day, let me zoom here. For each day, like for this day, what is the minimum simulated value? What is the maximum simulated value? So let me go back to the. So what I will do is I will select minimum of TCI, comma, empty brackets, comma 2. So if you remember this comma 2, it means that I want to have the minimum in each row, because each row represents one day. And then I want to have the maximum in each row. So basically now I have the range. Let me run this. And this opens up a new figure for me. What I will do, I will color the area under TCI range column 2, which is basically my maximum range. So what it will give me is basically, it gives me everything with the upper bound. So you see everything is colored with the upper bound and the lower bound is 0. But we have some situations for which our minimum was more than 0. It wasn't 0. So if I zoom here, minimum is basically 0 everywhere. Whereas, you know, it shouldn't be 0. Sometimes it's not 0. What I will do is I will color the area under the minimum with white. That will take care of everything being blue. So not this one. This one, what happens? Oh, all right. So okay, so I have to click on this one, and then I have to run that again. Not this one again, but this one. Okay, so if I zoom in now here, you'll see that minimum is not 0 anymore because we removed those zeros and we have the minimum value. Or we basically colored it as white. That's what we did. Let me actually close that other one. Let me work on this one. And then we also wanted to add my observed flow ones, and I wanted to add access and X label and box would be on and everything. So what I will have is basically now the blue area is basically my area between minimum simulation and maximum simulation. And when I say minimum simulation and maximum simulation, remember we have 1,000 different parameter values. For each parameter value, we'll have a different simulation for each day. So we sort for each day, or we sort based on what is the overall R squared value, and we select the best simulations based on the R squared, and we select the minimum and maximum of those selected streamflow values, and we see how many of these observed points, these red dots, are between the minimum and maximum simulated values. This is so that's part of the thing that we'll do. But one of the things that was asked was, what is the range of uncertainty, or what is the average range of prediction? So for each day, I have an upper bound and a lower bound. I have an upper bound and a lower bound. This is my uncertainty range, or this is the bound of or this is the simulation bound. What I will do, I will calculate this lengths for each day, and then I'll take the average of all days. So that's my average predictive uncertainty range. What I will do is this TCI column 2 minus TCI, or TCI range column 1, this was the maximum for each day, and this was the minimum for each day. So maximum minus minimum, and average of that will give you, this is the uncertainty range, 8.32 cubic meter per second. That's the uncertainty range for each day. And then I also asked, what is the average R squared for the selected simulations? So R squared, again, we only selected the first 1,000, or the best 1,000 simulations. So we will take the best 1,000 R squared values and take the average of that. And the average R squared value is 0.34. Then the other thing that I asked was how many points are covered in this range. So is there any point that is outside of this range or not? So as you can see, all these points in here are between the range. So all the points are lower than that maximum, upper than the minimum. What I will do is I will find how many of my simulations, how many of my observations, which is flow, are more than or equal to the first column in range, which is basically the minimum simulation, and how many of them are less than or equal to the maximum, which is the second column. So we will find how many are more than the minimum and less than the maximum, and we divide it by lengths of flow, because that's how many points I have. So we'll see what is the percentage of points that are within this range. If I run this, you'll see that I have 1, so that's 100. Basically, if I want to get that in terms of percentage, I have to do 100 times that value. And if I run this as expected, I will get 100%, which I get 100%. The last thing that I asked was, how many of, or what is the percentage of flooding, or what is the hazard probability of flooding? What does it mean, a hazard probability? First of all, flooding was defined as 40 meter per second. So whatever is above 40 meter per second has a probability of flood. So what I will do here, I will add hold on, which I had before, so I didn't really have to add that. I will plot between 1 to 1096 days I have, and then 40 and 40 was basically my flood line. Line width of 4. That's my flood line, because I just want to look at the figure and see how many points are above that flood line. So this is my flood line, and as you can see, there are a bunch of points that are above, or there are a bunch of days that we are above flood line. This is one of those days that our simulation is above flood line. This is one of those days. This is one of those days. This is another day. This is another day. This is one. This one. This one, and this one. Now the question is, what is the probability that I will have flood? Because I have so many simulations. I have, so same day for this one. For the same day, I had here and I had here. Actually it didn't really go above the flood line, but you never know, maybe it goes. Our model might be wrong. We want to be conservative. But we want to know what is the probability that we go above this flood line. Probability of going above the flood line is basically how many of these simulations per day are above this flood line. So for each day, let me show you TCI index. So we have 1096 days and we have 1000 simulations for each day. We want to know how many of these 1000 simulations are above this 40. We want to find the probability for that. Probability means how many of them are above 40 divided by how many you have per day. So if I want to find the probability, call it probability of flood, that's basically this TCI underline IDX. Is it above, more than or equal to 40 or not? If it is more than or equal to 40, we'll have a 1 for that day and that simulation. Otherwise, we'll have a 0. Then, as you know, for each, so days are rows and simulations are columns. So for each row, we want to know how many of our simulations are above 40. Basically, we need to add them up row-wise. So sum of TCI, because we have zeros or ones. If it is 0, then 0 plus 0 is 0. That's all right. If it is 1, it means that we are above 40. So we want to keep adding to that. So 1 plus 0 plus 1 plus 0 plus 0 plus 0. It tells us at the end of the day for each line how many simulations are above the flood line. We need a comma 2 here because some will do column wise and we want to do row wise. And then since we have 1000 simulations, we need to divide it by 1000. So this will give me the probability of flood for each day. If I evaluate this, see, I get a bunch of zeros. That's of course what I should get. So day 1 is 0. Obviously, let me make it smaller. So day 1 is 0, day 2 is 0, everything is 0 all the way to here, all the way to day 190 or so. So I will scroll down all the way to day 181 and 182. That's when I have a probability of 0.005. So that's 0.5% probability that I will have a flood this day. And then I have nothing all the way to day 200, I don't know, 10, 20, 222 and 223. So here I have a probability of 0.006 and I have a probability of 0.003. And then it goes all the way. So I have a couple of these days, or quite a handful of these days that you have a probability of flood. And then what I would like you to do is to have it in, write your report, and in your report, let me see. In your report, what I'd like to see is this flood probability to be shown. Like, see, just you can do it in the PowerPoint. You can just put a text box and say probability of flood is equal to 0.4%. That's it. Probability of flood is 1.1%. That's it. And then I would like you to do all this. And what I'd like you to do at the end of the day is basically to write a report, just a page or two. Each two of you will have, you'll have to submit one report only, and then write what you have done, basically what I've been discussing in this video, and give me a plot like this. Mean uncertainty width is basically that what we calculated, mean R-squared value, and coverage, and just that plot of the flood probability. That's all you need to submit, and best of luck. You have this video, so come back to the video and learn from it. Best of luck.